All right, we're back again. And this time we are going to take a look at something we've learned a little bit about, but we're going to now expand upon it and get a better appreciation for how it can work in a broader sense. And that something, of course, is gravitational potential energy. Let's look first at what we have learned so far. We know that the force of gravity was quantified by Isaac Newton. He was able to determine that the force of gravity, the newtons of force that are between two objects due to their gravitational attraction, is G times the mass of one object times the mass of the other object divided by the square of the distance between them. And so if we have two objects, and we'll call this one mass 1 and this object mass 2. If we look at their centers, that's assuming that they're basically uniform bodies, but we won't get into that, don't worry about that. There's the distance between their centers, r squared, and so there is an attractive force sort of pulling these two objects together towards each other. And of course our friend G is the universal gravitational constant, 6.67 times 10 to the negative 11. And of course it has weird units in order for everything to work out properly. This constant has units of Newton meters squared per kilogram squared. But often we just trust that everybody knows what they're doing, and when those newtons, or those units end up in here, they produce newtons for the force of gravity. And we learned that. Now we also learned that we can take a shortcut. We learned that if we look specifically at being on the surface of the Earth, and we'll draw the Earth here, ta-da. Well, if you're anywhere on the surface of the Earth, then your distance from Earth's center is basically the radius of the Earth, which is 6.38 times 10 to the 6 meters. And that actually is, even if you get in an airplane and fly above the Earth several hundred or even 1,000 meters up, on this scale, you're still not much further than this radius away. So when we say at the Earth's surface, I always tell students that it means from the ground up to where airplanes fly and everything in between. That's basically this far away from Earth's center. And of course, the mass of the Earth is something that doesn't change. Maybe I'll put little e's here. Radius of Earth, mass of Earth. Well, the mass of Earth does not change. It's 5.98 times 10 to the 24 kilograms. Huge. And of course, our friend G does not change. I've already written him up here. These three things here are unchanging if we are talking about being at the surface of the Earth. And so what we said was, if we take one of these masses to be the Earth's, and the G and the distance as the radius of the Earth, when you multiply these three numbers and divide by the square of the distance, you end up getting the value of 9.8, which is what we ended up calling little g, which is basically a shortcut for dealing with gravity on the Earth's surface. And so that shortens our little equation to the force of gravity equals mass of an object, m, times all those other things, g. As long as you don't go too far away from Earth's surface, that's fine. Good. Then we said, well, if that's the force of gravity, then the energy associated with gravity would be the force of gravity times the distance that you are applying that force through. So if you were lifting up an object and you were applying a force upward, the force that you must apply to lift an object is a force equal to its weight, which is the force of gravity, which pulls it down. So lifting an object up, and if you were to lift an object up through a height of, say, h, that would be the distance through which it moved. And so we sometimes rewrite this in other terms. Fg is mg, and h is the height that we move it through. And we can see how much work we have done. What we've actually calculated when we do this is the relative difference between energy in these two heights. but we haven't really specified what the starting energy actually was. We generally call it 0, right? But it's not necessarily 0. We go 0, and then we say, let's say we move from 0 to 10. Well, we call that a change of 10. But that could be the same as if I started at 20 and went to 30. It's still a change of 10. So this is kind of a relative formula that gives us the relative change in energy from two positions, from one position to another. But it doesn't tell us precisely what exactly, well, what is the real 0 for the Earth's gravity? Well, the real 0 for Earth's gravity would be the center of the Earth. So this equation is limited to situations that only occur near the surface of the Earth, and it only really tells us the relative change in the gravitational potential energy. So what we want to do is we want to try to come up with another formula that will tell us precisely what the energy value is with a common reference point, so that it's more precise. And we want it to be something that works not just at the Earth's surface, but everywhere in the entire universe, and not just Earth, maybe on the moon, or at the center of a black hole, or something. All right, so let's take a look at how we can get this to work. Let's go back to the force of gravity equation again that Isaac Newton left us with. G m1 m2 over r squared. Newton himself was completely unsure of what the mechanism was. What is the mechanism for the force of gravity? He knew how much. He knew that if you put in these numbers, you could figure out the magnitude of the force, and you could figure out the direction in which it acted. But what actually causes things to attract? If there's two objects here, and they suddenly feel compelled to move towards each other, well, what is that? Is it a rope? Is it an invisible rope? Are there a whole bunch of tiny leprechauns holding hands, pulling these objects together? What was the mechanism? And Isaac Newton honestly admitted that he had no idea. He did not know what could possibly be causing this attraction. He was only able to measure it and give us a reasonably good number as to how much it would be. So the next thing we want to do is try to see if we can come up with at least an idea of what the mechanism hiding behind gravity might be. And this is difficult because it took Einstein the better years of his life to come up with his general theory of relativity in order to explain all this. So we're just going to look at all that very, very, very broadly to get us a picture in our mind we can use. All right. So first of all, we have to get a concept of what space-time is. Space-time. Now in your textbooks, they won't get into this part of it very much. They'll just give you the formula and the equation and they'll say, go, solve the problems. But that doesn't really tell you much about what you're doing and why it works. Now we're not going to study relativity in detail right now, but we are going to approach it from that kind of a conceptual approach because it's important to get some background. What does space-time mean? Well, let's think about the two words. We have space and we have time. Well, basically we can put them together in this way. Think very simply of space as having 3 dimensions, right? If you graph space, it's kind of hard to do on a board like this because it's 2D, but we also have, think of that as coming out towards you, that dot. And we traditionally call these coordinates, x, y, and z, which in a sense can represent length, width, and height, right? It also shows that inside space you can move left and right along the x-axis. You can move up and down along the y-axis. And you can move in and out along the z-axis. So it basically describes all the different ways that you can move, and any combination of those. And of course, time is simply another number that gives us an idea of when you happen to be in a certain spot. So if we were to pick a spot in the universe, right here, we could find out what x, y, and z coordinates went with that spot. X, y, and z, which would locate it, and then we could say a time, and the time will be relative to something, but you could say at 4:30 p.m. On a particular day, on a particular year, depending on how you wanted to reference your time. Well, put all that together, that's space-time. It's where you are and when you are. Now, it's very hard to graph. It's hard on the graph. Like, how do you add this part into the graph? Well, it's difficult. It requires a 4-dimensional graph. And what the heck would that look like on a 2-dimensional board? It was hard enough for me just to draw this part and make it look right. We still have to struggle with that. But imagine if you could put all of these things together. All right? Now, take them all together, wrap them all up, scrunch them all together, and what we're going to do is we're going to visualize that it's just this line represents all of those things all wrapped up inside of it. And the reason I'm doing this is because we can't visualize what it would actually look like. So we're going to pretend that this line represents, if you could open up this line and unpack it, it would have length, it would have width and height inside of it, and it would also have time. And that's hard to imagine, but this way we can visualize our understanding of how gravity might work. So normally, if you're out in the middle of nowhere, far in space, and there are no planets, there's no mass and no energy of any kind floating around, then space-time is what we call flat. So we call this the zero energy level. You can kind of think of it as zero gravitational potential. Turns out there's other kinds of energy that might be hiding here, but in terms of gravitational energy, there is none. Now I want you to pretend that this is like a rubbery sheet or the rubbery surface of a trampoline. And what I'm going to do is I'm going to take a large bowling ball like this, say a mass of some kind. Put some holes in the bowling ball there. And I'm going to let the bowling ball rest on top of this rubbery sheet that we're calling space-time. Well, what would happen is the bowling ball's weight would cause the sheet to bend. And so the sheet would begin to take this shape where it bent down like this. And then it bent back up again. And it bent like this. We'll call that our zero again. And so here we'll make this a red bowling ball, and I'll make it a little smaller. There it is, sitting there on the sheet. Right? Looks like a head that's been decapitated, but it's a bowling ball. Perhaps yeah. Wow, okay. So we can see how the weight of this has caused the sheet to bend. Now, if we have a little marble right here. Now the marble will make a little dent as well, wouldn't it? But it would be a very small dent that would hardly be noticeable. So we can almost ignore the dent of this little marble and what effect it might have. Now the marble is rolling on the sheet. It's better if you think of this as a marble that was actually inside the sheet. I know that sounds weird, but remember, that line is space and time, so it's hard to imagine how anything could exist outside of it. We don't even notice it. All we notice is that this little green marble would roll along. And if he was rolling along, he would roll along the sheet, but suddenly he would start to feel this movement, this tendency to follow the sheet downward. And what would happen is he would be pulled down towards where the bowling ball was. And if he was heading straight for the bowling ball, he would be like, whoa, crash. And that's very similar to an object that's being pulled into the earth. Now, what if I look at this from the top? Okay, so now here's my sheet. I'm looking at it as if I was a bird looking down. And here's my bowling ball. But the bowling ball is sitting inside a dent. Now, the dent is going to just look like a sort of a circular shape, right? You can't really see a dent from the side or from the top like this. Now, if that marble rolls in here, there it was, it goes like this. But as soon as it gets close to the dent, it feels this little hill, and it rolls faster. It's like, woohoo, and it accelerates inward, just like falling objects, and crashes with the earth. Now, if I take this purple marble, and I roll it, but I roll it sort of off the center this way, what would happen is the marble would come in, but it would hit the side of the dent, and it would begin to sort of roll and spiral around the dent until it collided like this. So its path would suddenly come in and spiral around like this until it collided with the Earth. Now this is where our little analogy, our little model breaks down. We're talking about a model of gravity, and we're putting all of space-time in this line that we've drawn, this black line. And we're talking about a bowling ball, but it's gravity that's pulling it down, causing the dent. So it kind of doesn't make sense. I mean, we can't have gravity explain why gravity works. So imagine what would happen if you were out in the middle of space, and this wasn't a bowling ball on the Earth, but somehow putting the bowling ball in its place caused the space and time around it to bend. Not because it's heavy, but just because it is what it is. Then, what would happen is something a little bit different in the middle here. Remember, there's no more weight, so take weight out of the equation. We're just describing a red bowling ball that by nature of its being a bowling ball, it causes space-time to bend around it. Now when I roll my marble in from the side, you wouldn't see much difference for the other marble, but when I roll this purple one, it was purple, into the side, it's going to roll around and around and around and around. But see our picture up here? Because we're not talking about weight, there's nothing to pull it downwards in towards the ball anymore. And it'll roll around and around and around forever. And of course, when you look at this, you think, wow, that's just like the sun and a planet Earth or a planet Mars that just goes around and around and around and around forever. It's like the sun has somehow made a dent in space and time. And as Earth flies by, it gets caught in the dent, and it continuously goes around and around and around in a circle. And so this is kind of how Einstein explained what gravity actually is. It's not actually a force at all. It's a bit of an illusion. What happens is that masses, large masses especially, cause the space and time around us to dent and bend and warp. And when they do that, things that are moving near them tend to fall into the dent and move in circular patterns towards their center or in circular patterns around them. And there's all different possibilities of how you could ride down this hill. You could ride around in circles. You could just go on a weird angle this way, that way. There's lots of things that could happen. But basically the idea of gravity is that there's a bend and things get pulled into the dent. There's a dent in space-time. Now why does it look funny to us? Well, it's because we can't perceive anything over here or here. We can't even perceive the dent. We don't even know the dent is there because remember, our entire existence is inside this black line. So we have no perception of the dent. So it's a dent in a dimension that is greater than the 4 dimensions we can sort of imagine. It's a higher dimensional dent. And once you get your mind around that, you can kind of see, at least, how this gravity could work. Now, how could we have a dent in a dimension that we can't even imagine? Let me try to give you some insight into how that could happen. There was a time, thousands of years ago, when people who went for a walk along the Earth, oops, we don't want that, on our pen. When people who went for a walk along the Earth, especially if they were out in a field, they realized that Earth is pretty flat. The ground is pretty flat. Sure, there's bumps and there's hills and there's valleys, but generally, if you walk across the Earth over a great distance, it's flat. In fact, if you were to take your truck and drive from, say, California across the country to Vancouver, or to not Vancouver, New York, and California, well, you make a pretty flat straight line. But eventually, people figured out, when they started to see shadows of the Earth on the sun, they started to see boats sailing off into the horizon and how funny it looked as the boat appeared to sink down. They started to realize that Earth is not flat. Earth is curved. It's a circle. So when you walk over large distances on the Earth, you're not walking on a flat surface. You're walking in a curve. But those early people, before they realized that the Earth had this extra dimension to it, they thought they were moving flat. And someone watching them would see them move along this curved line from the outside, but you have to be standing back and be able to see the whole Earth and all of its curving. So if these people could walk along and feel like they were in a flat world, but in actual fact they were making a curve and didn't know it, you can see how it might be possible for us to be moving around on our flat space-time, but not noticing that there may be an actual dent in it, but we don't notice it at all. So, now that we've described this, let's use this picture to illustrate something about gravity. Let's draw our dent in space-time. And let's say that our dent represents, let's put the Earth down here at the bottom. Now, what I'm going to do, normally the marble or the bowling ball would rest in the dent, but I'm going to draw the Earth sort of like this, because this is not an actual dent. It's not a sheet. We use the rubber sheet to give us an idea, but it represents the bending of space-time. And I'm going to put the center of the Earth at the bottom of this particular line. All right? So now, instead of representing space-time, our line is going to represent the amount of gravitational energy. And 0 is when there's no dent or bend. 0. 0 joules of gravitational energy. All right. If we look at our picture, extend that a bit. If we look at where the surface of the Earth is, it's right here. It's a particular height above the bottom of this dent. We call this dent, we give it a name, we call it an energy well, because it looks like, when you dig a hole in the ground to dig a well, it's like a hole. It's downward. All right, so here's where I'm at when I'm standing on the surface of the Earth. If I throw something up into the air away from the Earth, even if I throw it extremely high, now on this picture it's hard to draw to scale, but let's just say I can throw something all the way up here. Let's draw a little blue line or green line. I throw something up, way up to there. Well, now it's at a new position in the well. And this change represents the change in the gravitational energy. It's kind of like I crawled out of the well a little bit. The object moved upwards out of the well. In fact, you could even think of it as a little person who crawled up the side of this hill from here to here. In order to do that, they would have to change their energy. And of course, when you change energy, you have to do work. So we would have to do work on this particular object or on this man to move them up the well. So when we throw things up in the air, we give them energy. All right? When we throw things up, we give energy, which is kinetic energy. That's how we give it energy. And that kinetic energy then allows it to move upwards in the well. Now remember, unfortunately, we're talking about a well that's below the level. So if this is the 0 level, then all these numbers down here would be negative numbers if we had a graph, right? If it was a graph showing the levels of the well. So it turns out that down here, you're at this depth, it would be negative. This is a little bit less negative, say right here. This is even less negative, and if you could climb right out of the well, you'd end up at 0. You'd end up at 0. So we would expect that any kind of formula for figuring out gravitational energy should indicate that the energy caused by Earth's gravity is negative. It's below the normal line, or below the resting line of, it's below the resting or 0 line. So that's one of the things that's interesting about this well. The energy caused by a mass is a negative energy. All right. So how can we figure out what kind of mathematical expression we might be able to get? Right? I should mention too that Think about throwing something. If I throw something up in the air, it falls back down to earth. If I throw it a little faster, it falls back down to earth. I throw it a little higher, it falls back down to earth. There is a possibility that if I was really super strong, I could give it enough kinetic energy by throwing it super fast that it would actually rise out of the well. What would happen to our man if he had enough energy to climb up here and get out of the well? Well, when he gets to this height, he falls back in. When he gets to this height, he falls back in. But eventually, when he gets up here, he's able to keep on going and no longer feels like he's going to fall back in. And so what we say is he's been able to escape from Earth's gravity or escape from the well. And there is a certain amount of energy that you can use to do that. As long as you have enough kinetic energy at the start to get you all the way out of the well, you could actually escape. And this, of course, this is how we travel into outer space and get away from the Earth. Okay, so let's talk about mathematically. That's enough conceptual. What we need is now to figure out how we're going to come up with a way to describe what we've just described, but with math and not just words and pictures and rubber sheets. So to do that, let's take a graph, a good old graph. And let's examine the force of gravity. Remember, Fg equals G m1, m2, 1, 2 over r squared. Let's graph the force of gravity, the strength of it here. And let's graph the distance away from the center here, r. Well, when you are very close to the Earth, say down here, very close to the Earth, where r is very small, you're right near the Earth's surface, or maybe even underground, you're very close to Earth, the force of gravity is fairly strong. So let's put a dot up here to show that it would be a fairly high force of gravity. But as you get away from the Earth, if we take a distance way over here, well, the force of gravity is going to be much smaller that far away. So I'm going to put my dot very low. So let's see, not much gravity force here. And if you connect the dots, well, if you connect them with a straight line, that would not be quite accurate, because if you look at the equation, remember, if this was an r on the bottom, it would be a sort of a direct relationship and it would be a straight line. But if it's an r squared, it means it's a curvy line. And so what actually shows up is a line that looks something like this. And if I'm extra careful, it's kind of hard to draw this, but the axes become like what we call asymptotes. And so these lines get closer and closer and closer and closer, but never actually touch. Right? So what that means is, as you get further and further away from the Earth, the force drops to pretty much zero. But it also means that as you get very, very close to the Earth, the force of gravity goes up, 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 and it would go infinitely high if not for actually colliding with the Earth's center at some point. So at some point there's a limit to how high this force of gravity can get for Earth. All right. So that's our graph of what would look like. We graphed force and distance. Now remember that work equals force times distance, and work is energy. So the energy associated with gravity could be thought of as the force of gravity multiplied by the distance through which the gravity is working. And that happens to be the distance between the objects, same as this. Well, guess what? If you look at this graph, if you were to take a measure across here, which is r, and a measure up here, which is force, if you wanted the area of a block, say like that, it's force times distance, F times r. Which means that on this particular graph that I've drawn, the area represents force of gravity times distance. So that means that the energy is equal to the area under this curve. Well, that's getting us close. How can we figure out the area under this curve? Well, again, just like we did with relativity, we have to look at this theoretically and not get into too much detail, because many of you have not seen any calculus yet. If it was a triangle, we could do 1/2 base times height. If it was a square or a rectangle, length times width. But it's not. It's a crazy curvy line. So Isaac Newton figured out what to do. And I'm just going to show you what he did without getting into the details. He said, let's take this curve and let's draw rectangles, little ones. And so if we draw these little rectangles, and we draw them along the curve like this, okay, and we keep going all the way along, then the rectangles give us sort of, if I could find the area of those rectangles, it would be sort of the area under the curve, wouldn't it? But it's not perfect, because you see there's all these little bits sticking up here that would be extra. Well, Isaac Newton found a mathematical way to make rectangles, but that were a little bit smaller. If I were to make smaller rectangles, then the little bits hanging over would be even smaller. And if you could make rectangles that were infinitely small, then the top of the purple step would be exactly the same as the curve. And so that is a mathematical process called integration, which is something that has to do with calculus. And the symbol for doing all that is a big S-shaped thing. It's called integration. But we're not going to learn how to do integration because it takes many years for students to learn calculus at that level. However, we can just trust in the magic of the mathematics. And so what you would say in math is that if you took a force curve, a force of gravity curve, and you found the area under that curve, then that would be the same as, whoops, better go back to black. That would be the same as the area under a curve generated by all this. G, oh, black again. G, M1, M2 over R squared. And so what this means is we're just taking the area of this graph. And of course, through the magic of calculus, this becomes the area under the graph is the energy, the gravitational energy. And when you do the magical mathematics associated with these funny integral signs, this side of the equation turns into negative G M1 M2 divided by R. Not much different at all. But that's what it comes out to. So we can use this clever mathematics to derive this. Now, here's what makes students nervous. It makes me nervous as a teacher. There's two formulas now that you have. You have the force of gravity between two objects, which looks like this, R squared. And you have the energy between two objects due to gravity, which looks like this. And the R is not squared. Very easy to confuse the two, to make a mistake and put a square where you shouldn't. So you have to be very vigilant. Also, watch this guy right here, and watch this guy, the negative sign, which is in one and not the other. To make matters worse, eventually we're going to start using little subscripts like 1s and 2s down here, 1 and 2. And of course, if you are doing something really quickly on your test or on an exam, and you see a little 2 down here, you might mistake that for a 2 up here, and you might square it by mistake. So you can't do that. You got to watch very carefully. All right. We have a little bit of an understanding, sort of how energy exists because it bends space and time around us, and we can figure out how much it bends space and time around us by using an equation something like this. It actually tells us what the level of energy you would be at. So let me just draw my little curve. Here's your space energy well for a particular object with a large mass in there. And then what this equation tells you is it tells you which level are you at. If you get 0 for this, it means you're right up here at the top and you're out of the well. But if you get, notice the negative sign, notice how the math knew? The math knew that gravitational energy needs to be negative without us even telling it, which is interesting. Anyway, the answers to this equation, the numbers you get, tell you what level you're at in the well, right? What R, basically it's the R is the height that you're at. So this tells you what energy level you would be at. Okay, let's do a simple example question then and we can be done with it. So let's take a question and say that how much work is done in moving a 1,000 kilogram spaceship or satellite or something. I think I'm writing spaceman in there. Spaceship. Spacecraft. How's that? From Earth's surface, because that's where we tend to launch from. It's where we live. We want to move it from Earth's surface to a height of 200 kilometers above the surface. We have to be very careful now about what our zero is. Remember, our zero for all of this, our bottom line for height now, is the center of the Earth. But we still have the surface here because that's where we live and that's where we do it. So let's draw a picture just to be safe. Here is the Earth's gravity well. And let's just put the Earth in at the bottom. There's the center of the Earth. Here's where our rocket starts. Let's call this position 1. It starts on the surface of the Earth. So you can see it already has some gravitational energy. It's not zero because it's not at the center. We're going to shoot it up into the air. I won't draw it to scale, but we're going to put it up here at position 2. So that's where the rocket ends up. Okay? 200 meters higher. 200 kilometers, sorry. Now, because it's not to scale, it looks kind of funny, but the distance here is 6.38 times 10 to the 6. Whoops. Remember, that's the radius of the Earth, right? 6.38 times 10 to the 6. And then there's an additional distance being added on to that for the second position, which is 200 kilometers or 200,000 meters. Remember, we need to make sure we do everything in standard units, meters and meters. So the height of position 2 above Earth's surface will be the sum of these two numbers. And when you add those numbers together, they come out to 6.58 times 10 to the 6. So that is what R2 is going to work out to be. R1, the height at position 1, or the distance between Earth and the ship at the start, is the radius, and then later it's this entire height, which is adding them together. So now that we see what we've got, we can write out the math and plug it away. So the work done is equal to the change in energy, right? Don't forget the work is equal to change in energy. Well, we are changing gravitational energy, Eg2 minus Eg1. That's what delta means. 2 minus 1 tells us the difference or the change in the energy. All right. Now, I'm going to have to use a lot of space here because it's going to get a little bit nuts. Negative G M1 M2 over R. That's what we said the energy was equal to. Then I'm going to put the minus in right here for the, because we had said that we're doing the difference. That's because of the delta, right? But I'm minusing another negative number. Negative G M1 M2 over R. Now, I'm going to put R2 here and R1 here. Notice that none of them are squared because we're talking about energy. All right, so that doesn't seem too bad. Let's see if we can't do some math here. Before I do some math, to make it easier, because we're using big numbers with scientific notation, I'm going to factor out some stuff here. I'm going to factor out minus G M1 M2 out of both of the terms in this equation. When I factor that out of this first term right here, I'll be left with a 1 on the top and an R2 on the bottom. R2, not R squared. Now, if you look at what's happening here, these two negatives are going to make this eventually become a positive number. But I'm factoring out a negative. So that's making the whole thing negative again. Two negatives make a positive, factor out a negative, and it's negative again. And that would be 1 over R1. So that just makes it a little bit easier to put all the numbers in. Then we put in the numbers. Oops. We put the numbers in. And I'll just bring that back so we can see it a bit. We put in the numbers. Here they are. Work, or change in energy, is negative G, 6.67 times 10 to the negative 11. Put brackets around it. Mass 1, well, that would be the mass of the Earth, 5.98 times 10 to the 24. You can look that up, or you write it on your sheet somewhere. You'll use that number a lot. That's kilograms. The mass of the spaceship in the question was 1,000 kilograms, so I'll put that in there. And then I have to multiply all of that by 1 over R2, which we said was 6.58 times 10 to the 6. Not squared, just, that's it. And remember, that's R2. That's the distance from the center of the Earth to the second position, right here. So we had to add the 200,000 onto it. Notice how we can't just say that, well, we'll say the bottom is 0. Can't do that. And then 1 over the original 6.38 times 10 to the 6 is the Earth radius when we were on the ground. Okay, now you can crunch out all these numbers, and if you do, you will get, depending on what kind of significant digits you use, you will get about somewhere in the value of 1.9 times 10 to the 9-ish. And it will come out to joules. Okay? I'm going to say about. If you use your calculator and you round off differently, you'll get close to that number. That basically means that it takes 1.9 times 10 to the 9 joules of energy to lift this spaceship from the Earth's surface to a higher point in the energy well, a higher point off of the Earth, 200 kilometers up. And that's basically how we use this formula. There are lots of other ways you can use it, but as we do more examples, we'll take each one as they come. And that's pretty much all we have to say about that.